Live? Yep. Hello and welcome to the second Porous Media Tea Time Talks. With these seminars, we want to give junior researchers working on porous media the chance to present their work to the scientific community around the world. This is meant to be complementary to the geoscience and geoenergy webinars, which you can find in our featured channels. My name is Tom Bultrees from Ghent University, and I'm here today with my co-organizers, Maya Rucker from Imperial College, Kamal Singh from Heriot-Watt University, Mohamed Noura from Oslo University, and in spirit as well by Marcel Moura from Oslo University, who unfortunately cannot join us due to the time difference. We do vary the time of the talks to accommodate speakers in different time zones across the world. And with that, I'd like to hand over to Kamal and Maya, who will be chairing today's session.
So I think you haven't heard me. So yeah, thank you very much, Tom. Yeah, I will immediately start now with the first speaker. It's a pleasure to introduce you to Chenhao Sun. He is a PhD candidate at the University of New South Wales, Australia, and he studies fluid dynamics in porous media, which includes the characterization of wettability and its relation to multiphase flow phenomena, which he is going to talk about today.
Okay, thank you, Maya. I would like to firstly thank the Porous Media and Tea Time Talks team to give me this opportunity to introduce my research in this webinar, which is characterization of wettability using topology and integral geometry in porous medium. Okay, so as we know, the wettability of the solid surface is a key property and has attracted broad scientific interest in nature and technological process. This interest is motivated by many applications in engineered systems, such as hydrocarbon recovery in subsurface rocks, fluid transportation during energy or carbon storage process, or the high-level radioactive waste storage in geological systems. So to this end, recently there's a community forming around the wettability characterization by mainly focusing on the contact angle measurement in porous medium with advanced in microcity imaging technology. So we recently developed a methodology to characterize the wettability in porous medium by using the principles of topology with the collaboration with Steffenberg in Shell, James McCullough at Virginia Tech, and Anna Henry at ANU. So due to the time limit, I will mainly focus on these 3 key points that this community may be the most interested in. The first point is the surface homogeneity, which is common in the porous median and subsurface rocks. One factor complicating the understanding of wetting phenomena in these complex systems is the effects of contact angle hysteresis due to the surface roughness and chemical homogeneity. You can see these two SEM images. So the traditional concept of contact angle, which is a purely geometrical measure related to the curvature, is often used for categorizing the wetting state of multi-phase system. It can be determined from the Young's equation by applying the equilibrium thermodynamics, but it's well established that the contact angle hysteresis lead to the apparent contact angle differ from the intrinsic contact angle given by the Young's equation. So the microscopic contact angle measured by the direct local method at each surface contact point can vary from point to point along the contact line. These effects, together with the errors due to the image resolution and segmentation, could produce a wide distribution of observed advancing and receding contact angles. So it's very important to capture these effects of surface of the microscopic contact angle is limited because it only measures the contact angle hysteresis and provides the phenomenological information for the technological applications. So we don't know whether the contact angle is still a representative measure in the complex system with significant homogeneity. To close this gap, here I will introduce a methodology to evaluate the wettability by imaging the total topology of fluid cluster in the system based on the microcity imaging technology. We use the Gauss-Bonnet theorem to establish a direct link between the curvature and the contact angle based on the newly defined term, the deficit curvature. Since we believe that the topology of fluid interface is the most intuitive way to represent the bending behavior of the solid surface, or the macroscopic wettability in a more rigorous word. For a multi-phase system, the Gauss-Bonnet theorem can relate the total curvature of a fluid interface to its topology as measured by the Euler characteristic. The deficit curvature is defined as the summation of the geodesic curvature along the contact line. It corresponds to a total angle of change along the contact line based on the contribution to the total curvature of the fluid interface as a result of its topology due to the wetting behavior of the solid surface. To make the connection between the deficit curvature and the contact angle, we normalize the deficit curvature by the number of contact line loop we can obtain the macroscopic contact angle for the entire fluid droplet. For more detail, you can refer to our recent published paper in Geophysical Letters. To demonstrate how this method can capture the effect of the surface homogeneity, we use a simple system, which is a sensor drop on the rough solid surface to provide a proof of concept. We compare the average of advancing and receding contact angles in rough capillary tube for different intrinsic contact angle, from the work of Morrow to the theoretical results of macroscopic contact angle I just mentioned. So this figure shows the strong agreement between the macroscopic contact angle, which is this red line, and the average of advancing and receding contact angle for both experimental data, so which is this black dot, and the hysteresis model, which is gray dot line. So it can be conclude that the macroscopic contact angle accounts for this macroscopic contact angle variations, which is the contact angle hysteresis. A lot of people may ask, so this method can take the average effect of contact angle hysteresis caused by the surface homogeneity. Is there any other advantage? I would say yes. So we can perform an analysis to test the image resolution effect by taking this flow cluster as an example. We downsample the image of the droplet by halving the resolution twice. It's intuitive in this figure how the downsampling impacts the droplet interfacial curvature and the shape of contact line. It also has a great impact on the macroscopic contact angle values. But for the macroscopic contact angle derived from the deficit curvature, there remains a basis to obtain the deficit curvature as long as the topological structure of fluid interface and the number of contact line loop is captured. So the deficit curvature is less sensitive to the resolution effects, which is particularly attractive as a way to capture the batability on the rough surfaces and tight rocks, where sub-resolution homogeneity and the limitation of image resolution present. Another advantage this community may be interested in is that this method can provide a single value of contact angle or a universal metric to represent the vanishing state of the box system. It's beneficial to be used at the input for direct numerical simulation for multi-phase flow. For this analysis, we can sum up the total deficit curvatures for all contact line loops to obtain the total deficit curvature for the system. We can also obtain the total number of contact line loops for the system. So by applying the equation we developed, a single angle, macroscopic contact angle, to describe the writing state for the box system can be achieved. Okay, so to conclude, I have introduced a new batability characterization method, which is deficit curvature. I have talked about this method can account for the average effect of surface homogeneity, and it also less sensitive to the resolution effect. It also can be a universal metric to describe the better state of the box system. Okay, so that's all. Any questions?
Thank you, Chenhao, for this great presentation. In the meantime, people are typing in. Please type in your questions if you have any. I would like to ask a quick question. Have you tried it on any sort of data which is available, for example, for mixed vector cases?
No, I think it's absolutely important for mixed wet system. This is what I have done for now, and we now I'm currently working on analyzing mixed wet sandstone to see how this impact on the mixed wet systems. Yeah.
Sure. Thank you.
Yeah.
We have one question coming in. Just give me 1 second.
Okay. May I ask a question?
Absolutely, yeah. Please go ahead.
Chenhao, so you mentioned that the method you use is not so sensitive to resolution. Are there any other aspects in terms of the experimental setup which you need to consider for this type of analysis? Where are the limitations? What is the quality which you need?
Sorry, you mean the image resolution? Sorry, what's your question again, Maya?
When you conduct the measurement, what is it what you need to look out for to make sure that the quality is sufficient for the measure to be taken properly, to be accurate?
Sorry, the signal is not. I cannot hear exactly what you are asking. Yeah.
What do you need to look out for during the experimental measurement to make sure that the quality is sufficient for the measure to be taken?
Yes. So actually, for this question, I actually haven't, taking this. We haven't tested this because we actually don't know how this, this can be done. This, yeah. Probably need to consider this in the future. Yeah.
Okay, we have a question from Aryan. He says, thank you for a very nice talk. How would you distinguish a system where some of the surfaces are water wet and some surfaces are oil wet? For example, would it be possible to calculate more than one angle? It goes along with the same similar question. Yeah.
Yeah. I think for more than one angle, you mean actually it's another question for mixed wet system, right? Because our method is, I think it's independent. So we take the whole, I think it's independent of, the water wet, oil wet, or mixed wet. We only take account for the total fluid interface as a whole, and we only measure the geometry of the fluid interface. So no matter, say, here is oil wet, or here is water wet, and it doesn't matter. So we only, for one cluster, we measure macroscopic contact angle, and for another fluid cluster, we measure the macroscopic contact angle for that cluster. And for the total system, we can sum up all the deficit curvature to determine the bulk bending state for the whole system. So I think this is yeah. So
Sure.
I think, yeah.
Sure. We have another question from Abdul Rahman. He asks, how would you make sure the segmentation is correct?
That's I think that depends on, because we use a visual to or some other technique to do the segmentation process. I think because this is another maybe it's independent from my my work. So I think
Sure.
yeah. So
I think with the new techniques, for example, machine learning techniques are getting really popular.
Yes,
And we can improve the segmentation.
now because in our research group, there's we are now carry out machine learning process to do the segmentation for the rock types and to account for several minerals in the rock. So I think it's pretty much good for.
Yeah, I think there's some recent nice papers on machine learning, comparing machine learning with other algorithm for segmentation, and
Yeah,
they prove it. It's really comparing not only the qualitatively for images, but also with different parameters.
yeah.
Okay, I don't see any questions, so I would like to thank you again, Chenhao, for your time and for this great presentation. And we wish you good luck for your future work.
Thank you.
Yes. So we'll now move on to our second talk of the session by Shabina Ashraf. Shabina has recently completed her PhD in chemical engineering from IIT Delhi. She works on multi-phase flow in porous media, interfacial phenomena, and data science. Today, she's going to talk about spontaneous intubation in layered porous media. Thank you, Shabina, for joining us today, and the floor is yours.
Okay. Thank you, Kamaljeet, for introducing me. I'm Shabina, and thank you, Porous Media Tea Time Talks, for making me a part of this series. So, today I'm going to speak on spontaneous inhibition anomalies in stratified layers. So, this is the theme of the presentation. So, I would like to present my work describing the capillary impregnation in layered porous media. So, initially, I would like to start off with homogeneous porous systems. In homogeneous porous systems, so these are three homogeneous porous systems, and when a wetting fluid is placed, the imbibition capillary invasion begins, and it is well known that the larger pores will have a fluid front that travels faster as compared to the other smaller pore systems. And in addition, it also follows diffusive dynamics, where the square of impregnation length is proportional to the grain size diameter and also the time. So this is a length versus time plot of the impregnation phenomena. We see that the large pores have the leading front, and so this is a log-log plot of the dimensionless distance versus time representing the same. So therefore, for a homogeneous porous media, the larger pores will have a fluid front that travels faster. But the real porous systems that we encounter, like in oil reservoirs or soil horizons, they are made up of several layers. So, and mostly they are not homogeneous. So, in such cases, these strata have different properties, different pore sizes, different capillary pressures and permeabilities. In such cases, are the diffusive dynamics still applicable, which are applicable for homogeneous porous systems? And in those cases, also the fluid front in the large pores will still lead. To investigate this, we constructed a layered porous medium. So the S indicates a porous layer which has small pores, L indicates large pores layer. So we have conducted two experiments, and in both of these experiments, we found that the small pores are always having the leading front. So this is contrary to the observation in homogeneous porous systems. But why does this happen? They don't even follow diffusive dynamics. Why such contrary behavior is observed? To understand this, we went ahead and performed some volivofluid simulations in ANSYS Fluent, and these gave us some really good insights as to why such a phenomena occurs. So, two of the inferences from the simulations that proved out to be very important are: one is when both the layers are occupied with the same fluid, the pressure drop is the same. So here we can see that the pressure drop is same when both the layers are occupied with the red fluid or both the layers are occupied with the blue fluid. And another inference is that we have observed some fluid transfer between the layers, and this mostly occurs only at the menisci location. So these are the streamlines from the simulations. And so now we have two inferences of the pressure, the same pressure drop when they're occupied with same fluid, and the fluid transfer at the front locations. So by incorporating this into Darcy's law, we have developed a one-dimension model. Now we wanted to see if the one-dimension model necessarily mimics the experimentally observed phenomena. And yes, for both the cases, our one-dimension model was able to mimic the experimental observations. So this blue line and blue markers in both the cases, which are for the small pores, they are leading. So in a two-layered porous medium, the small pores will always have the leading front. So, but the actual porous media that we see are multi-layered, and with multi-layers, there will be complexities that arise. So, therefore, we went ahead to find what happens in a three-layered porous medium. In a three-layered porous medium, all these three layers can be arranged in three different ways. So this is case 1 where the small pores are in the middle layer, and this is case 2 where the medium pores will be the middle layer, and this is case 3 where the large pores constitute the middle layer. And for each of these 3 cases, by using the inferences from the volume of fluid simulations, we made 3 one-dimension models for each of these cases separately. So we also wanted to see what happens when we perform experiments on layered porous medium. So this is the case 1. We see that the small pores layer has the leading front. So again, blue line and blue markers are leading here. And so for the next case, here also the small pores are having the leading front, same, just like the two-layered porous media. And for the third case, we found that the medium pores are having the leading front. So it's not the small pores. It's not like the two-layered porous media. It is different from what we have observed for both these cases. Why is such an anomaly occurring? I mean, is this anomaly even possible? And if it is possible, what is causing this? And can we develop a one-dimension model that would be able to predict it? So we developed a one-dimension model, and to our surprise, the one-dimension model was very accurately mimicking the imbibition dynamics for this arrangement. And then we wanted to understand why even such an anomaly is possible. So if we go back to the inferences from the volume of fluid simulations, we find that for this particular case, the third case, the medium layer and the small layer are separated by the large layer in between. So the fluid in the medium and the small pores layer is not continuous, which for arrangement 1 and 2 we see that they are continuous, hence the pressure drop is the same. So we went further ahead, and using the one-dimension model, we have described the grain sizes of the layers during which such an anomaly is possible. And we also found the necessary conditions when small and medium pores will have a fluid front that travels with the same velocity. So more details on this could be got from this publication. So all in all, what we have is that small pores will not always have the leading front for a layered porous medium, and the leading front will depend on the arrangement of the layers and also on the contrast in the layer properties. So okay, this is for a 3-layered system, but the usual systems that we encounter again are multi-layered, and then every time the arrangement changes, we need to formulate the governing equations again. And for every single arrangement, there are several possible fluid front locations. Like for instance, I have shown here one arrangement of a 5-layered porous media. For this one arrangement, there are 8 different possible front locations. So that means we might have the need to develop 8 different one-dimensional, 8 different governing set of equations, and so this becomes a tedious task. So one 5-layered porous medium will have 60 such arrangements. So one arrangement is having 8 different possibilities, and there are 60 arrangements. So this becomes very cumbersome. So we went ahead and we generalized the one-dimension model. And the one-dimension model is able to predict the imbibition for irrespective of the arrangement, irrespective of the contrast in the layer properties, and irrespective of the number of layers. So using this one-dimension model, we wanted to see if this is still valid if this can be experimentally reproduced. So here we show the experimental validation of this generalized model for a 5-layered system, and yes, the generalized model predicts very well. And then we went ahead to analyze using a one-dimension model for 20 layers. For 20 layers, there are about 10 power 18 cases that are possible. So out of that, here I'm showing only 6 arrangements. And out of these 6 arrangements, we see at one particular time, which is 0.5 dimensionless time here, we see that the front is different in different arrangements. I mean, the front positions are different for different arrangements. And also, if we go through for the breakthrough time, the breakthrough time are also different for each of these 6 arrangements. The details on breakthrough time can be found in this publication. And we see that the smallest of the pores may have the front through which breakthrough occurs, or one of the considerably large pores indicated by this pink marker may also have a leading front, which may cause the breakthrough. So therefore, the time of breakthrough and the layer of breakthrough are dependent again on the arrangement and the contrast in the layers properties. So this is another graph showing the grain size of the layer through which the breakthrough occurs versus the breakthrough time. And we see that for 1,000 arrangements, which is shown here, the breakthrough time usually lies between 0.5 to 0.7. So it is different for different arrangements. And the grain diameter through which the breakthrough occurs can vary from the smallest of the pores to considerably larger pores. So therefore, in a multi-layered porous medium, both the breakthrough time and the breakthrough layer will strongly depend on the arrangements of the layers and the contrast in the layer properties. So in conclusions, we have that the front in the small pores always leads for a 2 layers porous medium. For a 3-layered porous medium, the small pores always does not have the leading front. And for a multi-layered porous medium, the contrast in the properties of the layers and the arrangement affect the leading front, the breakthrough layer, and the breakthrough time. So thank you for this opportunity and thank you for tuning in. And I'll be very happy to answer questions if any.
Thank you very much for the great talk. Certainly, if you have any questions, please just type it into the chat. In the meantime, I have actually one. Have you ever considered looking into patchy porous media rather than layered one?
Petri porous medium?
Yes, so instead of having the layers sorted to have patches of different,
Okay.
yeah.
I have not looked into patch porous media, but I think if a fluid front, propagating fluid front reaches one particular patch, it will follow diffusive dynamics until that patch is covered. So
Okay.
there are some studies on porous media which are not layered in the direction of flow, but perpendicular to it. So I think it would be something like that.
Thank you.
May I ask Maya one question? Curious if you have looked into wettability and roughness, it impacts a little bit and or significantly.
Yes, here we have controlled the wettability by treating the glass beads before doing experiments. We're cleaning them with acetone and bringing them to a particular pH so that most of the surface roughness is gone, and because it is glass, so we have considered it to be smooth here, and that all the impurities on the glass are washed off during the cleaning procedures.
Okay. So we have few questions in the chat. Here is one from Rayana Akbari. Do you see any effect from the capillary pressure or permeability contrast among the layers or mobility ratio?
Yes, yes. The capillary pressure is inversely proportional to the bead diameter. That is roughly we have taken from the literature studies. But otherwise, here instead of using small pores, medium pores, or large pores, in my publications I've mostly used the term capillary pressure and permeability because it would be complicated here. I have not used these terms. But yes, with the change in grain sizes, the permeability changes, the capillary pressure changes, and this one-dimensional model is very well applicable for mobilities ratios of the order 1 and 0. Yeah. So for high mobility ratios, I think the phenomena also changes. Yes.
Here's another question from Abdul Rahman. Were all these tests through spontaneous inhibition? What would happen if you have an inlet pressure?
Yes, these tests or these experiments were for spontaneous inhibition. This is purely a capillary-driven flow. If there were an inlet pressure, maybe in the equations along with PC will have an additional delta P. If it is a controlled inhibition, maybe minus delta P. So accordingly, the model would also change. But so far, we have not used it on inhibition or forced inhibition or controlled inhibition.
Another question from Ariane. Is the fluid arrangement also dependent on the layer thickness?
Fluid arrangement, if it is by fluid arrangement, if it meant the fluid front location, then it depends on layer thickness. But in all these experiments, we have considered same thickness because the manual packing was really tough, so we considered the same thickness. But yes, layer thickness makes a difference. But the fluid fronts have not changed much until 5-layered systems. They have not changed. However, for multi-layered systems, I have not investigated it, and that's a wonderful part to investigate. Yeah, thank you.
Okay, and that was the last question from Zaid Yangda. Is it possible to relate this dual porosity permeability system in hydrocarbon reservoirs?
It is possible to relate. So this, I have performed this on a very small scale. So the scale up of this, because this is the experimental setup is of the order of millimeters, centimeters. So I think performing certain scaled up experiments would be needed to answer this question. So it would be wonderful if they are relatable. Otherwise, I think there should be some corrections that should be, or additions, or more investigations that needed to be made. Thank you for this.
And let's thank the speaker again, both of them, for the great presentations from today. Our next sessions will be from Esosa Ekanem and Mohammad Masoudi on visualization of viscoelastic polymer solutions in porous media using microfluidics, and post-scale modeling of nucleation growth in porous media, a probabilistic approach. Further, I would like to, can you go to the next slide, please? Yes, yeah. I would like to make you aware of our email address, porousmediattt@gmail.com. If you have any questions, you can contact us there at any time. And also, if you want us to keep you informed about the next sessions, please just drop us an email and we will put you on the distribution list. With this, I would like to close the current session. Thank again all the speakers for the great presentations from today, and all of you for joining the discussion. I'm looking forward to see you in 2 weeks.